Thank you. We are going to go ahead and move to the next session. We have our keynote speak, Bryan Brewer, and the topic is going to be Composite Manufacturing and Hypersonic Technology. He is from San Antonio, Site Core and Engineering Manager, and currently working for Boeing Company.
Good morning.
Good morning, Bryan.
Should hopefully be sharing a primarily blue screen. I get that figured out right?
Yes, it's working.
It's looking good.
All right, good. So good. My name is Bryan Brewer. I'm with the Boeing Company. I've been with Boeing about 22 years now. Most of that time, about 16 years, has been with what we call extreme environment materials, materials that get hot, primarily non-metals. And that's mostly been supporting hypersonics, planetary reentry, hot exhaust wash structure. And so worked at most of the major sites. I'm currently now in San Antonio and really liking it here. So today I'll give a little bit of background just on the Boeing Company. Some people don't necessarily always know about the Boeing Company, but a little bit of background. About 105 years old. A lot of other companies have merged in together. Hughes, McDonnell, and Douglas merged in, and Rockwell International. So a lot of heritage with the Boeing Company now, but are the largest aerospace company in the world, and we are everywhere with our products and what we support. So anywhere in the world, you're going to find Boeing is going to be there in some capability. Primarily, Boeing broken up into three companies: your commercial airplanes, your military, defense, space, and security, and then global services, which is what I'm part of, which is kind of your service-oriented business of how to keep the products working and to repair and maintenance. And then there's a very tiny group, Boeing Capital Corporation, which is real estate, but very small part of the business. So we're a lot of people, about 140,000, which is down. We've been a lot higher in the past, but we are an engineering company. And so if there's an engineering field you're interested, guarantee that there is that opportunity somewhere in Boeing. But we are an engineering company, and all engineering is represented here at the company. So I want to get into, San Antonio, where we are specifically. We do MRO, so maintenance, repair, overhaul. We started off in the late 90s with C-17 doing repair and maintenance to keep that fleet viable and to keep them supporting our troops. Our site is pretty big. We have 1.6 million square feet. We actually just upped that about another 30% with another hangar that we've taken over, and that happened in the past month or two. But pretty big site. We are growing. Within the next 18 months, we're going to have 8, maybe 9 different platforms that will be on site between the executive fleet, B-52s, F-18, F-15, C-17. We're going to have a lot of programs here, and we are growing quite a bit. Big part of what we do, as I was saying, is how to repair these aircraft, which is very different from production. It's going in and either doing a modification to improve the performance of the fleet, or a lot of times going in and going, well, that's broken. How are we going to fix that? Which can be a big challenge, but it's a lot of fun also, because it's always kind of a new problem that comes in for us here. So a little bit about the San Antonio site where I am now. Most of my time I've had with Boeing has been, again, with hypersonics. And so I'll go just a little bit of the background of kind of composites. Most people think of Boeing composites is 777X wing CFRP. Composites, fiber, reinforced plastic. So these giant wing structures, and you have these machines that are just trying to lay down material as fast as possible. or like on the 787 barrel, you have your winding tape around a giant mandrel so that you can make a fuselage. And that's most of what Boeing does as far as composites. But where my world, and something a little different that I think is a little more interesting to talk about, is composites like the heat shield, where you have an ablator-filled honeycomb to protect the Starliner, and very similar on Dragon that SpaceX has, and it works well. It is kind of similar to also what Apollo had, but an ablator-filled honeycomb, still a composite type of setup. And then also ceramic matrix composites. So like jet engine nozzles, we're working on that. How do you get a nozzle made out of ceramics? Because the engines are getting hotter and hotter, and we have to be able to, and metals can't take those temperatures. We're already up to titanium and Inconel, and so we have to go beyond that with ceramics to be able to take the temperatures. As the engines get more efficient, efficiency a lot of times comes through increased heat, and metals just can't do it anymore. So that's what we're going to kind of get a little bit more into, kind of in a manufacturing example here, is that side, the hot structure, not necessarily the CFRP, the carbon fiber reinforced plastic type stuff that Boeing's normally known for. So hypersonics, again, that's where I've been. Kind of two types of hypersonics that I see is you have reentry vehicles, planetary probes, space shuttle, where you're just coming back into a planet's atmosphere, and you're going fast. I mean, at a minimum, if you're just in orbit like space station, you're coming in at over 20,000 miles an hour. If you're coming back from the moon or Mars, much, much faster, and that really increases your heating. The other type is what I call boosted vehicles that are air breathers. And these are just two examples that I've worked on, which was X-51 and High-Fly, which X-51 was a scramjet and High-Fly was a dual combustion ramjet, where you are breathing air in, mixing fuel, and then accelerating back out through the back of the vehicle. So it's pretty exciting work. It's continuing on now. Here recently, I think Lockheed and Raytheon had a flight of Hawk, and so it's very similar to X-51, but that's what I kind of consider hypersonics. And all these will require thermal protection systems. You get a lot of heating from the outside of the vehicle just because you're going through the air so fast that that air rubs against the vehicle and gets it pretty hot. So how hot is hot? I kind of like this slide. So, I mean, trying to understand how hot we get. Like, we get up to temperatures over 3,500 degrees Fahrenheit that we're trying to protect against. And like, for reference, when you're baking cookies, 350, I mean, that seems hot, but it's not. I mean, lava and steel mills are still lower temperature than the temperatures that we're trying to deal with going through the air that fast at Mach 5, Mach 6, or planetary reentry coming in. You get much hotter than normal things that we would consider hot. Before I get too much further, we'll get into the manufacturing example. Would love to have questions. If you can come off mute and you want to ask a question, or I'm trying to keep an eye on the chat. I think there's one in there in the chat. Yeah, okay. So trying to keep an eye on the chat. If you do have questions, please ask. Love questions. If we don't get through any more slides and just have questions, that would be great. So if you do have questions, please let me know, especially as we start getting into the manufacturing example. So moving on with hypersonics, as you're getting into your manufacturing of a hypersonic or planetary reentry, you've got to make some decisions on what kind of thermal protection system are you going to be working with. Are you going to have a single use, or are you going to be reusable? And so X-51 there on the left was a single use. It used an ablative, and the outside of the vehicle burned up. But as that vehicle burned up, it helped keep the vehicle cool. And you do have some erosion off the surface. So your vehicle gets a little less thick as you fly through the air, as you erode away that surface. So one-time use. Other side would be something like space shuttle. where you had ceramic tiles, can be a lot more expensive, but your outside shape doesn't change. And so if you're trying to use a control surface to change the direction of your vehicle, you can't have a shape that is that's changing on you. And so you'll have to have something that's like a non-burn away type of material like that. So those would be some of your major decisions before you get into your manufacturing. Next, you'll be needing to test. And so with testing, especially for these types of materials, we'll use some sort of accelerated heated gas. And so we use a lot of arc jet testing, where you have a test chamber that you pull down a hard vacuum, and then you'll have a nozzle that has a power supply, electrical power supply, that then under pressure blows down that superheated gas through the electrical core and gives you superheated gas at a very high velocity. And so that's what you'll see there on the right is a sample that's in that flow and getting heated, because it's very difficult to recreate hypersonic flow in a test condition, to be able to get that type of heating, that type of pressure, and then that type of air velocity to be able to give you the erosion off the systems. And so very difficult to test these types of materials. So we've made some decisions on what we're going to test or what type of materials, and now we're starting to test them. And so we're going to get into an example of a manufacturing example of it's called a reentry breakup recorder. And I like this example of a manufacturing because it's not overly complicated like a commercial airplane that's got just millions of parts, but it was a low-cost way to look at how do we gather reentry data from an uncontrolled reentry from space. At some point in time, the International Space Station is going to re-enter the Earth's atmosphere. It's just a matter of when, where, and in how many pieces. And we really don't have much data on what that heating environment is. So we don't really know what to test it to, and we don't know what those forces are going to be. But uncontrolled reentry of big pieces, they have come down and they have hit people's property, especially some of your like engine parts, power heads, which are real dense, that they can survive that type of reentry. And so trying to gather data on how do we get, what is the reentry environment that's uncontrolled? We know when we control like a spacecraft, we can control it, and we have a very defined shape that we have, and we can get data for that. But this is just something that's going to come in and bounce along as we go. Question about temperature sensors. I'll get to that. And they're called thermocouples, and it's two dissimilar metals. So it's welded two dissimilar metal pieces called a thermocouple, and they are embedded into the thermal protection system, and we'll see that here in a second. So as the reentry comes across, when it's uncontrolled, your footprint on where all this stuff could land is all over the place because you don't have it controlled. And so that's where we're trying to get better data, because we don't want all these pieces of something big re-entering, possibly coming down over populated areas. We want to better make sure that it's all going to burn up or it's going to be landing in the ocean. So this is kind of what it looks like. You've got a back shell and a forward shell. You've got your instrumentation, and then you've got communications. And so this particular one, it's designed to go up in a supply vehicle to the International Space Station, and it hangs out in the supply truck, and the astronauts unload the supplies to the space station, and then they put back in trash and things back into that supply truck, and all of that re-enters back into the Earth's atmosphere. And that reber, that rinse your breakup recorder, is part of that trash truck, and it just goes along for the ride. And and we'll talk about how it pops out and re-enters and makes a phone call basically as it's falling down through the atmosphere. It makes a phone call and to the satellites above and transmits all this data that it's captured and still capturing on the way down. It's not designed to be recovered. It wasn't planned for it to survive when it hit the ocean, but they did. And it was designed to be inexpensive. Again, we're putting it in with the return trash truck, and so really trying to keep it low cost, because this is just going to burn up and be a throwaway type of thing. It's pretty small, about a little bit bigger than a soccer ball. So again, pretty small. High level kind of flow of what we would need to do to manufacture it is we need to fabricate the back shell and the forward shells. We have to then machine those, and then we install the TPS, machine the TPS, and then we start getting into how do you install your electrical equipment and your antennas. And so you got to start figuring out how you're going to attach to your structure that you've created. Now you have a nice structure, but how do you attach to it? And then the instrumentation, thermocouples, that's measuring the temperatures up to these temperatures, measuring the temperatures in these environments, and putting and installing that, and then final nut plates on how to attach the equipment, and then we start closing it out. And we'll get into that example now. So the back shell, it was standard layup, pretty easy. It's a radio frequency transparent. We have to be able to transmit a signal. As we come down through the atmosphere, we got to transmit a signal back behind. And so this was just a standard layup, not too difficult. We just had a female mold, and it was hand laid up to be able to make a pretty easy part to cure. It was about 25 plies. And so you just lay down one ply, and this was what's called a 0-90 fabric. So you have fibers that are running into the 0 and the 90, and then we rotate around the clock orientation to give us what's called a quasi-isotropic layup. So it gives it strength, because those composites can only give you strength generally in one direction. So you orient your fibers to be able to give you the better strength. So pretty easy, simple piece to lay up. That's the back shell. And then the forward shell was a little bit more complicated, because we had to build a shelf. We had to build something that we could attach everything to. And so that's what you kind of see there in the left, is how do you make that shelf? Normally, if you start laying up around it and you put all this into your autoclave and cure it, it gets hard, you would be jig locked. You wouldn't be able to get your mandrel out. You would have to make almost like a Jenga type metal mandrel, which would be very expensive to make, to be able to pull out the mandrel. So what we ended up using is a washable mandrel to lay up on, which is basically sand with a binder in it. And so it's hard, and so we can lay up against it, and then we put it in our autoclave to cure it. But then when we're done with the cure, we just make a hole in the tape, and we can wash it out with water. And so that was a very low cost way to have tooling, because a lot of times tooling is very expensive with a project. But again, we're trying to keep it fairly low cost. And so that's how we got around having to have an expensive tool, was a washout mandrel. And so that's how we fabricated the bottom half, the pointy end going into the atmosphere. So and so this particular material is called BMI. It's bis moly imide. And so you have carbon fiber that's in there, but then the resin part is the bis moly imide. So it's a higher temperature type of resin, which can be, and this one's really challenging to fabricate, because as you get hot, your resin gets to a real low viscosity and it wants to squeeze out everywhere. And so that's our forward shell, and it's pretty rough. And so now we would need to go machine it to be able to start getting the holes in. So we machine, and we have holes that the machining composites. You don't cut as much as you grind, because when you're machining composites, you grind to be able to get a good surface finish. When you cut, those little fibers in the composite a lot of times will fray up on you and won't give you a nice clean edge that you can work to. So we fabricated the structure. Now we're machining the structure and putting our attach points in it so that we can start looking at how we attach the instrumentation to it. But after we've got that machined, we need the TPS that'll come on after that. So we can see the flat spots that we have, and we're ready to be able to attach equipment. But before we attach the equipment, we have the TPS. So this was the critical part. Again, it's getting really hot, and so how do we keep it cool? We line the outside of the leading edge. We bond on a honeycomb, and but we then need to fill all those individual cells of the honeycomb. And so back in the Apollo days, when they're going to the moon, they filled each one individually by sticking a nozzle down in and filling each one individually. It was very, very time intensive. And so what we worked on here was we filled just the couple in the front with a high density ablative material, but then on the rest of it, we just hand packed it in the outside. We wrapped it in a vacuum bag, and then we used the autoclave pressure to press it all in. And so now we're not having to go fill each individual one, but we can have an autoclave do that work for us. And that's how we get it all the cells filled at one time without having to go one by one. And so we've got our TPS in our honeycomb, and they machine it. And so we then start installing the thermocouples, the TC plugs. And so this is how we measure the temperature, is we have a wire that goes across at a certain height or in the thickness, and that wire will give you a difference in electrical charge between the two dissimilar metals. And that difference in charge can then be equated to a temperature. And then that gets fed into a reader that tells you what the temperature is. And so that's how we measure the temperature on the outside. We have thermocouples on the inside also, but that's how we measure those temperatures at the very extreme numbers, like 3,500 degrees. You have metals that can take those temperatures, yeah, that's how we'll measure those. I think that was one of the questions. So we have our TPS. Same with the back shell. We did the pushing in the ablative on the back shell the same way. And so now we're looking at installing the support equipment. But how do you do that? And a lot of times you have things like nut plates, and a lot of times those are fastened in with a rivet. But again, we didn't want to drill more holes in our structure, and we're looking for lower cost options. And since this is a one-time use, we glued them on. We used a high temperature adhesive, and with really good strength, more than we needed, up to 350, which is be more than enough. And so as we start wanting to install these things, you have a problem with composites and metals that they can't come in contact with one another for long durations, because you'll get a battery type situation, which will then start corrosion between composites and metals. And so anywhere you're going to have metals and composite touching, you got to put down something like dielectric tape or fiberglass to be able to act as a boundary layer between those two. And so that's what we start doing next before we start putting any of the instrumentation in, is we get those nut plates and dielectric materials put in. And then also we have to think about the aerodynamics now of the vehicle, and that this vehicle is self-righting. It doesn't have any control surfaces. It just controls itself through shape. And so we have to add ballast. And so we add tungsten to the nose of the vehicle to help give it a heavy point to help it go into the wind. Again, no control. It's just popping out with the as the vehicle destroys itself in reentry, it pops out on its own. Again, you can kind of see these nut plates because you've got to be able to screw down onto your structure. And with composites, you never really tap a composite like you do with metals. And so you got to put down something that you can screw down onto. And so again, nut plates, and we used adhesive to be able to hold it down in place. Trying again, going for lower cost type options. And so we've got our TPS, we got our thermocouple wires coming through, and we're ready to start loading in equipment to it. We can see the ballast that we added, that we talked about, to give it a heavy nose. And we do the final closeouts with the material. Again, you can see it's a small area inside there, and that's just regular electronics. It's not too much different than your cell phone. But the outside of this vehicle is going to be well over 2,000 degrees. And so you can see how thick the thermal protection is there to protect it, because you can't put your cell phone up to 2,000 degrees. It starts saying it's going to shut down if you leave it in the sun, and it gets up to like 100 or something like that. And so you can see just how thick that back edge, or how thick the thermal protection is. And you can see the leading edge, the gray and the green, are a lot thicker than the yellow, because you have much, much higher heating on your leading edges of your materials. And so we install our equipment. We then bolt the top half and the bottom half together, and then we fill in the holes with more ablative material, let it cure, and just give it a little bit of a sand to give it a smooth surface. And we end up, as you can see on the right there, a finished vehicle. With hypersonics and reentry vehicles, you can't have any gaps. Any gaps in the surface, you get hot gases that will enter your structure and will just destroy it. Those hot gases will cause your structure to fail very quickly. And so making sure you don't have any gaps in your vehicle is very critical for a successful flight. And so we have our finished vehicle there on the right. And so now it's time to go to the space station. You can see it's inside that copper housing. And they've unloaded the new supplies. They've loaded supplies back in. And that copper housing, the idea behind that is that you have copper, which is a very conductive, low melting metal, and that it would heat and melt, and it would release the vehicle very quickly and easily. But all that stuff around there is going with it. And so all of that debris is going along with the vehicle as it reenters. And so we did get pictures from a plane with a long lens. And so that's one of the vehicles returning back to Earth. And you can see there's just all kinds of pieces coming apart. And there is one of those reentry data recorders somewhere in that field. And we had success. We got data. It made the phone call and sent back the data that we got there of what were the Gs, what was the temperature, and then at what altitudes did you get those pressures. We also had some failures where we think one of the fuel tanks exploded during reentry, and we were mounted right on top of the fuel tank. And we didn't survive that one. We think it blew us apart and destroyed the vehicle before we got any data from lower altitudes. So we have had those failures, but that's part of the reason why we made them low cost, is that we can just keep putting them in and gathering data when we have the return vehicles that come and break up. I do like to point out that if you look at the actual reentry and then compare it to a test vehicle, we see that hot spot leading the vehicle, and then you have that cooler dragging out line behind it, and it's just a lot of similarities to which is what we want to see that our testing and real world are lining up with one another, that we see that same type of flow behind the vehicle with a hot spot that's leading it into the beginning. We did have one rocket that blew up on the pad, and so we didn't go up, and we just sat in the fire on the pad. We survived the fire on the pad, and so that's what those pictures are. But we have had other vehicles that survived the impact into the ocean, and they just floated on the ocean and sent their data back. I think it was for about 32 hours. It sent the data back. It just keeps making the same phone call over and over, sending the data and what it's seeing. And so we have had some successes, and we had some interesting ones where it definitely was a very intense heating environment, being a fire on the pad. But the vehicle pretty much survived. It obviously got charred up with that. Any questions? I know there's one about what are the typical research opportunities on this subject. So we do a lot of kind of this development research to develop these types of materials at Boeing. We do a lot of times work with universities, a lot of times to get some of the testing done, but we do a lot of it internally with what we develop. I have a few patents now on these materials so that we developed them, and then Boeing patents them so that we can use them in our products. What other questions are there?
It's a great presentation, Brian. I'm surprised you guys also do this research. This before you join San Antonio side, this is while you're there.
Yeah, we don't do this at San Antonio. I've done this more from other sites. I was primarily in a group called Boeing Research and Technology, where we did most of this development of these materials that we then do the development, and then we work with the programs like BDS or even Boeing Commercial to help them with integrating these materials in. We don't do hypersonics at San Antonio, but we do a lot in St. Louis. We do a lot of the development still in Southern California for the materials. But yeah, this was before I was here in San Antonio, but I just thought it was a good, concise kind of manufacturing example of from idea to finished product. So I like this one for our National Manufacturing Day.
Yes, we don't do hypersonic here at UTRGV, but we do have the other consortium site, UTSA. I think they have a pretty good hypersonic, system, testing system on campus. And I don't know if you've been working with them or not. If not, we can connect them with you, because I'm pretty sure you can learn a lot from your previous work. And
Yep. Yeah, I'm working with Dr. Combs and in contact with them and hoping to work more with them. There's a question on how do we verify the data is correct and accurate? So everything is calibrated to start with that we use. And so all these thermocouples that we see coming out, those are calibrated, and we verify from a standard. We'll test it, we'll put it into an environment at just 100 degrees, something low, and we'll verify that it's reading the correct temperature there against a standard. But the other part is that's why we want to get multiple sets of data, is that we can then verify it against other flights, other reentries, to tell us that the data is consistent. Where if we see that one time we're seeing data that it's over 3,000 degrees peak heating, and then we never see that again, and we're always generally only seeing maybe only 2,000 degrees heating, we would look at that and go, is that just an outlier? Did something happen to that vehicle? But generally, we make sure that everything's calibrated before it goes into the vehicles, and we verify that. with the equipment. And then also we try and get multiple sets of data so that we're not just relying on one time to say, oh, that's what the temperature is that we have multiple data sets, multiple flights to verify that that's what the data is. Hope that helps or answers the question.
I had a question, Brian.
Yeah.
Do you do any work on metal materials? I know this was more about the composite part of it for orbital reentry.
I do not do as much, but Boeing does definitely. Like we definitely had like on X-51, we had a lot of things that were composite, but then ended up having to turn into being metal. On the leading edges of X-51, maybe I don't know if you can see my mouse or not, but these were originally a composite. They were what's called a carbon-carbon, and they didn't do well in some of our testing, and had to switch it over to a metal. I think it had to end up being something like, I think it was columbium, very high temperature metal, very expensive. But still, most of our planes here at Boeing are metal. And I know with launch vehicles, we've done a lot of work with aluminum lithium, trying to get the weight out. But there's still a lot of metal development. My world has been more focused on non-metals, but Boeing still does a lot of development with metals, and also with welding and joining metals, because you still have a lot of metal. Even with your new planes, it's hard to beat. Like 777X, we talked about, it has a composite wing, but the trade studies, aluminum was still a better fuselage option. And so still going with a metal fuselage. But still, yeah, lots of development with the metals. Just I haven't done as much of that.
I have a question. A lot of the times our students ask if it's necessary to go into the aerospace engineering field to be able to work in Boeing, for example. Like, what advice would you give them, let's say, if they're in mechanical, electrical, manufacturing engineering?
So I was a mechanical engineer in school, and then our school didn't quite have a materials engineering program quite yet at the time. But it's really, any of the engineering fields is what you kind of need to really be an engineer. It teaches you more about how to learn as opposed to the specifics of the engineering. We have lots of people that started off with electrical engineering degrees, and they're doing structural work now with the vehicles. And so it's more about kind of learning those basic processes and principles, and less. I mean, once you start working in aerospace, it's less about what you specifically studied with that. I'd say the only thing that's a little different is probably software engineers do tend to stay doing more software, but electrical and mechanical and systems generally cross over quite a bit. And we even have a cement engineer, like a facilities, that's doing tags for aluminum structures with our vehicles. So it's really just kind of learning those initial principles. And then after that, you really can go anywhere you want with an engineering degree, doing anything in the aerospace industry.
Let me add a little bit to this. Is a very interesting presentation, first, Brian, and I mean, I think your question is also very important for us to clarify with the high school student when you are selecting your degree program. And the engineering title here, the more industry relevant title. It's not the type of engineering degree program we offer. This is more specialized, right, Brian? And
Yeah, I mean, so what we look for, like, no matter what the engineering, like we're hiring somebody new, we don't necessarily say you have to be a mechanical engineer. We're generally looking for like it being a hard science, physics or chemistry, or one of the engineering fields as really all that's required when hiring into engineering.
yes, and like at UTRGV, we have mechanical engineer, electrical engineer, and manufacturing engineer. So because I'm a professor at manufacturing engineering department, so I want to talk a little bit more about manufacturing engineer. But if you look at the engineering title here, Brian showing in his PowerPoint, you have material processes, right? Engineering that, you know, manufacturing engineering bachelor degree would satisfy the job requirement, right? Like a production engineer.
Yeah.
Production engineering is something relevant to manufacturing engineering and industrial engineering. So that's what our department is about. And also system engineering, test and evaluation engineering. These two, but the three, they're gonna be looking for students from manufacturing and industrial engineering, right? Mechanical and structural engineer, you're going to be looking at, you know, mostly mechanical engineer students, right? So, but again, I mean, the title you see in the industry, in the company, you know, they gonna be affiliated with the engineering degree we offer from the university. So, but industry title more specialized, and university engineering degree program are more, you know, generic, in my opinion. So, but I just want to explain this to the high school students.
Yep. There's a question on why do we have to stop using carbon-carbon composites? It couldn't survive the environment. The aero loads on it were causing it to break. And so without going, I mean, too long, yeah, the carbon-carbon wasn't surviving the aero loads. And so we had to switch to a metal that had basically better toughness. A lot of times your non-metals don't have as good a toughness. They have a lot of times some good strength and can take high heat. But if you hit it with a dynamic force, yeah, you really need that toughness. And so that's why we had to switch to a metal, was to be able to take the toughness for those dynamic loads. It's not just a gentle leisurely flight when you're going Mach 5, Mach 6, like when you're cruising along in a commercial airliner. It's much more jarring, and those aero loads and I guess it's not really turbulence, but kind of like turbulence when you're going that fast, it hits a lot harder. And with the stresses on that inlet, it couldn't take it. And so we had to go to a more durable. So hopefully that answers your question, Brandon.
Any more questions, guys? No?
All right. Well, thank you, everybody, for the opportunity. Yeah, hopefully we'll speak again soon. Thank you.
Thank you, Brian.
Thank you, Brian.